Okay, this is another example from the textbook that we showed earlier. It's from page 60, problem number 28. And it starts off with, given that AO is perpendicular to CO, those being the lines, it wants us to prove that 1 and 3, those angles are complementary angles. We start off with our given as usual. Then we have to think, what do we know if it's perpendicular? Now, this is where you can go different routes in different textbooks. In some textbooks, what I'm about to show you would not be allowed. In fact, I don't know if this particular theorem I'm going to show you appears in all later textbooks. If it doesn't, you're going to have to use the one we did in the previous example to get to a point where we know that the measure of angle 1 plus the measure of angle 2 is 90. We'll talk about that more when it comes up. For now, we're going to get started. Not every theorem has a name. A lot of theorems don't have it, and most teachers don't name every theorem. So in this book, I'll show you one here, which is Theorem 2.6. And in Theorem 2.6, the if statement is that if the exterior sides of two adjacent acute angles are perpendicular. Let's see if we have that. Are the exterior sides, AO and CO, of adjacent acute angles, 1 and 2 are adjacent and they are acute, are those sides, the exterior means they're on the outside, if those are perpendicular, then the conclusion must follow. And the conclusion for Theorem 2.6 is that the angles are complementary. So we're going to use that in this proof here. We're going to say that angle 1 and angle 2 are complementary. And the justification is what we just showed. You'd have to, in these cases when the theorem doesn't have a name, you have to write it out. And so it's if the exterior sides of two adjacent acute angles are perpendicular, then the angles, again, what angles? 1 and 2. Those are the ones that have the exterior sides that are perpendicular. Then the angles are complementary. Okay, so one thing you might be wondering is, why can't we just say that the measure of 1 plus measure of 2 equals 90? That's what complementary means. But that's not what the theorem says. The theorem says the angles are complementary. It doesn't say they add up to 90. It's your responsibility to take this word, now that you've defined it, complementary, or you've got it rather, and use its definition to say what you want to say next. And so step 2 is based on step 1. Now, keep in mind, we bypassed the definition of perpendicular lines. We could have used it. It would be a longer proof if we did. So that's why we didn't go that route. But you can go back to the previous example in this video to see what that would look like to get to where we're about to go, which is step 3. The measure of angle 1 plus the measure of angle 2 equals 90. Now, how do I know that this is true? How do I know they add up to 90? It's because they're complementary. That's the very reason. It's if complementary, then add up to 90. Right? That's exactly what we want. That's the definition of complementary angles. Let's find it again real quick. Definition of complementary angles is right here. And it says, in this one here, the A version, that if two angles are complementary, then their measures add up to 90. It's a direct application of the A version of that definition. So that's why step 3 is definition of complementary angles. Okay, let's go. What did 3 use? It uses step 2. It's because they're complementary. So 2 goes in the parenthesis and the 2 gets an X next to it. And we move on to think about how are we going to do step 4. Well, what do we want? Let's go back and kind of analyze that. We kind of made this progress. We want 1 and 3 to be complementary. So we'd really like it. What might come before stating that these are complementary? What might come is measure of angle 1 plus measure of angle 3 equals 90. you kind of sometimes want to think about what the previous to the last step in the proof will be. You can jot it down on scratch paper so that you can think about this is a secondary objective. Actually, this is the primary, but to get there, we need this objective first. Okay, so then how are we going to get 1 plus 3 equals 90? We have 1 plus 2 is 90. Well, what I would like, well, it's kind of obvious. I kind of don't want the 2, and I want to replace it with a 3. Gee, I wonder if there's a way we could do that. Look, 2 and 3 are what kind of angle? They're vertical angles. So we can say that angle 2 is congruent to angle 3. And this has various justifications from different teachers and different textbooks. Some teachers will just call it vertical angles. Some call it vertical angles theorem. It's actually probably the shortest theorem in all of geometry. It's if two angles are vertical, then they are congruent, right? It's pretty short. If vertical, then congruent. That's the basics of it. So, is it because the measure of 1 and 2 is 90 that 2 and 3 are congruent? No. That's why 4 does not rely on step 3. What does it rely on? Only the picture. The picture is what tells us that two angles are vertical. And so based on that, we'll put a little p underneath the 4, which means we now have two unused statements. Again, every teacher has a different ruling on what I'm about to tell you. Some teachers will say that you can go straight to the measure of angle 2 equals the measure of angle 3, and they will write it here. Some teachers will let you do what I'm about to do. I think you should do it this way, what I'm about to do, because this says, in the theorem, it says they're congruent. It doesn't say their measures are equal. Now that might be obvious, but you still have to state it. What I'm going to do is what my teacher allowed me to do in high school, and that is the measure of angle 2 equals the measure of angle 3 after a semicolon of this statement. Other teachers will make you write this on a separate line, and they'll make you justify it with step 5. The reason would be definition of congruent angles. Okay, so keep that in mind. If your teacher makes you do that, then that's what you have to do. Every teacher has different rules on this. It's not an exact science. Okay, next up then we're going to go to step 5. We have our measure of 2 equals measure of 3. We've got two unused statements. Neither has played the role of an if statement yet. Well, when you're building up multiple unused statements, try to combine them. Let's see, measure of 1 plus measure of 2 is 90. Measure of 2 equals measure of 3. Well, this is that, then that can be replaced with this. And that's exactly what we write. Measure of angle 1 plus measure of angle 3 equals 90. Now, could this be transitive? No, it cannot. Again, transitive has to be the entire side equal to something, which is equal to something else, which is equal to something else. We don't have that. We have the 2 in the middle of this equation. Only that is being replaced with measure of angle 3. Right? You can visually think of it as I'm crossing this out and the measure of angle 3 is going in there. That's a substitution. It's literally the English definition of the word. You're substituting, right? So then this is going to be substitution property of equality. Okay, then step 5 uses both 3 and 4 to make its statement. If I didn't have 3 and 4, I could not say step 5. So I therefore use both of them. And then we get to step 6. And we're right there. We said that this leads us to conclude this. We're basically done. Angle 1 and angle 3 are complementary angles. Why don't I put measure here for these? Measure of angle 1. Because the measure, to understand difference between measure of angle 1 and angle 1, think of it like you. You're maybe 14 years old when you watch this, if you're about the age you would normally do this at. Then is your name, let's just pretend you have a name like John. Nobody's named John anymore, but let's say your name is John. Okay, then is this John or are you John, right? And then on top of that, if John is 14, it's the difference between talking about John and talking about John's age. That's the same thing. It's like a measure of how old you are. This is angle 1. This is like John. It's like a person, a thing, but it's not a person. Okay, it's a thing. It's an object. But the measure of angle 1 is the measurement of that angle, kind of like 14 is the measure of John. Okay, so keep that in mind to understand the difference in those two. We get over here, that's why there's no measure here, and we can say, again, how do we know? It's the second version of definition of complementary angles, the one that says if angles measures add up to 90, we can conclude they're complementary. Again, it's if measure of angle plus measure of angle equals 90, then complementary. That's exactly what we have here with 5 playing the role of the if and 6 playing the role of the then. So we put 5 in parentheses underneath the 6, meaning that it got used in our repeated if-then statement. Again, remember, every proof is a collection of if-then statements. That's all it is. The whole thing is a consecutive sequence of if-then statements. All of it. That's why the conditional statement is so important to be able to understand how to progress through a geometric proof. Let's go to another example. Okay, the fourth example of this video. It's from page 88, problem number 24 of that McDougall-Little textbook. Okay, so in this one, we have 2 givens now. Given BE bisects angle DBA, and angle 3 is congruent to angle 1. We're trying to prove that CD is parallel to BE. So how do we begin? Well, let's start with the givens. Is there anything we can get from them? If I was to say angle 3 is congruent to angle 1, the only thing that I would be able to say in step 2 with that starting point is that measure of angle 3 is equal to measure of angle 1. What are we going to do with that? I don't know. Let's leave it alone for now and let's go to the other given. That is that BE is a bisector of angle DBA. And if I start with that, that has another word that is defined in geometry. And that is, when it says bisects the angle, we have to think that this is like a bisector. Of what? Of an angle. Therefore, it's an angle bisector. There's also a segment bisector that you can have, or an arc bisector for that matter. So I'm going to go back to here, and I've got definition of angle bisector right here. And you can see it's got 2 versions. The first one would be if I know I have an angle bisector, then I can conclude that there's 2 congruent adjacent angles, right? That's the situation I'm in. I know that I have an angle bisector. I don't yet know that I have 2 congruent adjacent angles, so that's what it leads to. If angle bisector, then 2 congruent adjacent angles. Well, which 2? Well, look at angle DBA. It's BE, this line right, the segment right here, is the bisector of this angle. Well, what's it splitting into 2 equal parts then? Angles 2 and 3. So that's the second step. It is angle 2 is congruent to angle 3. By what? What did we use? We used the definition of angle bisector, right? Right? Can't do it upside down. This one, definition angle bisector. So that's what you write for the reason. That's why making a list of something like this for all of your proofs is absolutely essential, right? You should have one for every chapter, and as you go through geometry, you should be keeping a new list. Every time you go through a new section, add all the definitions, theorems, and postulates from that section to this. Right? It'll make your life so much easier as you progress through your homework and the class and whatnot. You're going to have to invest a little bit of time in geometry to fully understand proofs. So don't be afraid to invest that time, and consequently, if you don't invest the time, expect to not understand what you're doing a lot of the time. Okay, so then angle 2 is congruent to angle 3. That was based on step 1. Again, this thing that we're doing, if you haven't followed along earlier, is not in a textbook. There's no textbook that teaches you to do this. There's no other teacher that says to do it. This is my personal method that I have my students do to understand what is happening in a proof behind the scenes, right? So what you see if I cover this up, that's what your teacher sees, right? But these things, this is the background. It's like the scaffolding on a building, right? It's the stuff used to build the construction, which is the proof as a final form. Okay, so when I use step 1, I put the X next to it to indicate that it's been used. So now what do I do? Well, okay, we don't know what we're going to do with this just yet, right? But we know we're trying to prove that CD is parallel to BE. Let's think about what might come right before that. So right before what you're trying to prove, there's the step right before it, right? What you're trying to prove goes here, or the last step, and this is the last step minus 1, the previous step to the last step. It would probably be, look at what we got with the angles. We've got angle 1 and angle 2, and you should know those are alternate interior angles. Gee, if angle 1 was congruent to angle 2, we would have the information we need to show that those lines are parallel by the alternate interior angle converse theorem. Okay, so then let's try to achieve this objective, and that will lead us to this objective. So what do we want? We want 1 congruent to 2, and we have 2 congruent to 3. How are we going to get there? Well, that's where the other given comes in. You haven't used it yet. When you're kind of stuck and you haven't used all your givens, go to the next one. Angle 3 is congruent to angle 1, and the reason, again, is given. If you're doing a proof where they give you the reason over here, but they don't, or the statement, but they don't give you the reason, look at your givens sometimes and see if it's given. It's usually free points when that happens. Okay, so 3 is based on a given, so I put G here. I did not use step 2 to make step 3. It's not because 2 is congruent to 3 that 3 is congruent to 1. It's because it was given to us as free information. So step 4, we have to now think about steps 2 and 3 have not been used in our collection of sequential if-then statements. So we should be thinking, how can I use them? Well, let's look at it. 2 to 3 to 3 to 1, that's like the transitive we talked about earlier. So we can use that right now. We can say angle 2 is congruent to angle 1, and the reason is transitive property of congruence. Okay? And that's, could you make step 4 if you didn't have step 2 and step 3? No, you could not. You need both of them together to be able to make step 4. So you'll put 2 and 3 in parentheses here, indicating that 4 used those 2 steps. We cross out 2 and 3 or put an X next to it to indicate it got used as an if statement. Now, once you've given the justification to a then statement, because this is the then statement in the last if-then, once you give this justification, this becomes an if statement, right? It's an if statement right here, and it's if this, then this. So if angle 2 is congruent to angle 1, then segment CD is parallel to segment BE. And the reason is, again, let's see if we can find it on here. Okay, there's 2 theorems that involve alternate interior angles, right? There's the alternate interior angles theorem, which if you look is right here on my list, alternate interior angles theorem. And the if up here, the if is if it's parallel. So do we have that situation? Do I know that it's parallel in step 4? Because step 4 is the if statement, right? We don't know it's parallel. So don't put alternate interior angles theorem here. It's not going to be correct. But there's something else that uses alternate interior angles theorem, and that is called the converse of alternate interior angles theorem, right? So it's if alternate interior angles are congruent, then the lines are parallel. Do we have that? We have angle 2 congruent to 1, and they are alternate interior. Therefore, we have satisfied the if portion of that theorem. And we can say then that this must be true based on the converse of alternate interior angle theorem. Sometimes you can just write AIA for some teachers. That's what I'm going to write here. You might have to write it out for your teacher. THM is often abbreviation for theorem. Okay, so this uses step 4, and look at your proof. If you've done it correctly, everything should have an X next to it but the last step. Why? because that's what you're trying to prove. Therefore, it will never be used as an if statement. It is the final then statement. Okay, let's go one more example and that'll be it. Okay, this will be the last example for this video. If you like these examples of proofs and you want to see more because you're either going to take geometry, you're going to teach geometry, and you want to see more about how this style works of doing proofs, or if you're in geometry currently and you would like some more examples so that you can gain a better, deeper understanding, please request in the comments below. Otherwise, I probably won't make more videos of this type. If you like it, give it a like. That would be great. If you're an educator, please share it with other educators in whatever forums you have access to if you think it's good. Okay, so we've got here from page 125, again, in case you skipped this part of the video, this is the book I'm using. I absolutely love this book. One of the issues with newer geometry textbooks is that they really cut back on the proofs. This book has like a very high emphasis on proofs. It made it a really important part of the curriculum. A lot of the new textbooks just don't do that anymore because for some reason, whatever bodies that be, educational decisions were made that proofs aren't important or something like that, which is absolutely absurd. They're the most important part of geometry. Hopefully you get a teacher that makes you do a lot of them because they're the best part. Okay, so step one. What are we going to start with? We've got AB parallel to DC, or we've got AB congruent to DC. This comes from chapter 4 of this book, by the way. We've advanced a little farther forward, and now we're talking about triangles that are congruent. Okay, so what can we do with AB congruent to DC? Not a whole lot. You could say the length of AB is equal to the length of DC, but that's about it. So probably don't start with this given. Let's start with the parallel lines one. So we'll start with AB is parallel to DC. Now here's another tactic that I like to use. A lot of times in proofs, your picture will be two or more triangles combined. Let's think about triangle ABC and draw it separately so that you can look at what you have in just one triangle without clouding that picture up. Okay, so we know, in a minute we will know that AB is congruent to its counterpart in the other triangle, so we'll mark it here. Now we know that AB is parallel to DC. We will need this picture for that. We also get a freebie in this problem. Because our triangles share a side AC, you're going to at some point probably say that AC is congruent to AC. That'll be a reflexive property situation. So since we're going to eventually have that, what else do we need? Well, let's go through the ways that we know to prove triangles congruent. We have side, side, side. Is there any way to get BC is congruent to AD? Nope, no way you're going to get it, not from parallel lines, not from this being congruent. You're just not going to be able to do that. Actually, I guess if we had access to parallelogram information yet, we could do it because this is enough to prove that's a parallelogram and you could extrapolate from there. But at this point in this textbook, that knowledge didn't exist yet, so you wouldn't be able to use it. Okay, so then if we can't get this side, 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 side is out. Well, we could get angle, side, angle, but we don't have any angles yet. And we've got two sides, so we probably don't want to use that one. We can do side, angle, side. Well, if we were going to do side, angle, side, there's two sides here. What angle would it be? It's the one in the middle. It's got to be this angle. Let's mark that angle here. It's this one. And how can I make that angle congruent? What would it be congruent to? It would be congruent to the A matches with the C in the other triangle. So it would be this angle up here, and lo and behold, those are alternate interior angles, and we know they're congruent because AB and DC are parallel and AC is the transversal. So we would say in step 2 that angle, and you can't call it angle A, even though it looks like you could here, in the main picture that's not possible. We have to use 3 letters to name it. Okay, so it's angle BAC is congruent to angle DCA. And that will be alternate interior angles theorem. Not the converse this time. The converse is when you don't know lines are parallel and you're proving them parallel. The regular theorem, the non-converse version, is when you know the lines are parallel and you're proving the angles are congruent. Okay? So it's kind of like a biconditional, but not really because it's not a definition. Okay, so then, so then what are we going to have? Step 2, did it rely on step 1? It absolutely did. We only knew this was true because this was parallel, right? If we didn't have the parallel, we couldn't make this statement, so that got used. All right, let's advance forward. Now, even though we marked these 2, we actually haven't put them in the proof yet, and we're going to have to do that. So let's go ahead and go to the next part of it. We'll just write AB is congruent to DC. AB is congruent to DC as our other given at this point. And that's this one. Now we need the AC, so we're going to say AC is congruent to itself, and that is reflexive property. Now, of congruence. Now, again, you might be saying, why do we have to say this? Isn't it obvious? Yes, it is. You still have to say it. We have to justify the usage of SAS. And SAS says that I've got 2 sides and an angle in between them. Well, if I don't have the sides listed in my proof that are congruent, I cannot use SAS. So as tedious as it is and how you might think it's silly, you do have to write that AC is congruent to AC, and that is reflexive property. Now, this we're just going to put an R underneath again. 3 was a given, so we put a G underneath. Look at what's happening. We've got 1, 2, 3 unused statements in our if-then chain. So we probably need to use them, and we're going to use them all at once. It is very common when you get to proving triangles congruent that you will build up 3 unused statements, because most of the ways to prove triangles congruent have 3 letters. The other one is AAS. The only one that has 2 letters is HL. Okay, so 5 is going to be combining all of these. Now it's this picture that we have, and now we can make what we're trying to prove. Triangle ABC is congruent to triangle CDA. And the reason is, we've already circled it, side, angle, side. It uses 2, 3, and 4 all at once. We put them all in parentheses underneath. Again, most likely, no teacher is going to make you put these parentheses statements down here. They're just not required, and they're not in the textbook or anything like that. It is just the method so that you understand the background, what's happening behind the scenes in a proof. Okay, so you used all 3, and the reason is SAS theorem. You can say triangle congruence theorem, or however you want to write it. We'll just put SAS THM. Okay? I hope this helps. If you have any questions, please comment down below. I respond very quickly. If I'm sleeping, I'll do it as soon as I wake up. I hope this helps. You guys have a good night.